Again, welcome to Mathematical Structure for Computer Science, CS113. Also, the course is known as Discrete Mathematics. In these lectures, we're going to discuss about predicates and quantifiers. In our previous lecture, we discussed about propositional logic, and this is the continuation of it. We may have a propositional functions which must include variables and quantifiers. So we'll go through what is a variable, quantifiers, predicates. The quantifiers, we have two types. The universal quantifier. Universal quantifier means everything. Existential quantifier means some. And also we're going to discuss about how to negate quantifiers. Then we will go through some examples how we can translate English to logic, propositional function, using variables and also the quantifiers. So propositional logic is not enough. That's the first statement we have here. We went through what is a propositional logic in our previous, and normally in propositional logic, we have sentences, and we may express it still in words, but in our propositional function, we may also include variables and the quantifiers, predicates. So let's see one example here. We say all men are mortal. Socrates is a mortal. So this will follow that logically, then Socrates is mortal also. Since Socrates is a man, Socrates is a mortal. Because all men are mortal, Socrates is a man. So if Socrates is a man and all men are mortal, logically, then Socrates is also a mortal. But this can't be represented in propositional logic. We need a language that talks about objects, their properties, and their relations. So kind of the concept, mathematical models or expressions. So we may need at least variables. Then the two types of quantifiers we are going to use is the two types we call the or and also the sum. We may discuss that one later on. So introducing predicate logic. Here we see a predicate logic uses the following new features, which we didn't discuss earlier. That's variables. The variables can be X, Y, Z. It can be any letter. Then a predicate. A predicate is more or less a function in algebra or college algebra. So here we have P at X, M at X. It can be J at X. Let's say J is Java class, X are students. I can represent J at X as students taking Java class. Then also we may have quantifiers. So quantifiers, again, only two types we are talking about, or and also sum, which all means universal. Then sum is the existential. So propositional functions are a generalization of propositions. They contain variables and also the predicate. Example can be P at X. So in this case, X can be variable, P at X is our predicate. Then variables can be replaced by elements from their domain. So if we say X have values that is greater than 10, then this means the domain of X will be 11, 12, 13 going. Or if we said X have values less than 0, then it can be any negative value. So propositional functions become a propositions and have true values when their variables are each replaced by a value from the domain or bound by a quantifier, as we will see later. The statement P at X is said to be the value of the propositional function P at X. For example, let P at X denote S is greater than 0 and the domain be the integers. So this is example. If we say the condition here is s is greater than 0, then p at -3 is false, because again, -3 is less than 0. P at 0 also is false, because the condition is s is greater than 0, not 0. Then P at 3 is true. Why? Because 3 is greater than 0. And often the domain is denoted by U. And normally U, sometimes we use the term universal when we talk about sets. So in this example, U is integers. Again, U is integers. So to be the universal set, let's say here we say s is greater than 0. So your universal set are the values 1, 2, 3, 4, infinity, greater than 0, we don't know. So often the domain is denoted by U. So in this example, U is the integers. So example of a propositional functions. Now we say, okay, let x plus y equal to z. So that is our expression. Then we donate this by r at x, y, and z. So again, s comes first, y second, then z. Then we say the u can be for all the 3 variables. It can be any integer values, b integers, any integers value. So now we have this statement. We want to know if it's true or false. I have the r at 2, -1, 5. Remember, r is at x, y, z. And the condition is s plus y is z. So 2 plus -1, 5, that's false. So false. Now 3 plus 4 is 7. Okay, so that's true. So R 3, 4, 7 is true, because 3 plus 4 is 7. Then here we have R at x. X is a variable. It can be any value. 3, then z can be any value. So since we don't know the actual value for s and z, these are variables, we say this is not a proposition. We cannot decide whether it's true or false. Now we have another example. Now let s minus y equal to z. We are donating this by the predicate q at x, y, and z. So s value comes first, y second, and z, with u as the universal values, and these values are integers, so it can be both positive, negative, or numbers. So let's see the first example. We say q at 2, -3, q at 2, -1, and 3. This is true. Why? Because 2 minus -1 will give me 3. 2 minus -1, become positive, so 2 plus 1 is 3. So that's true. Now 3 minus 4 is not 7. 3 minus 4 should give me -1, so this is false. Here again, we have a variables, so we cannot decide. It's not a proposition. We also have what we call the compound expression. Compound expression means we have more than one expression now, and we can combine the 2 expressions using binary operators such as the and or we use the term disjunction and conjunction. So if I have a condition saying that p at s donates s value should be greater than 0, we should find these true values. I have p at 3. This is or disjunction. So p at 3 or p at -1. Remember, with the or, when one condition is true, our outcome is true. When 2 conditions are true, our outcome is true. We only get false when both conditions are false. So this will be true. Why? Because s is greater than 0. So p at 3 is true, but p at -1 is false. So true or false, the answer is true. Now here we are using the and or conjunction. And remember, the only time we get true is when both conditions are true. So p at 3 is true, but p at -1 is false. So true and false, the answer is false. Then next we get implication. Implication means when the left side is true and the right side is true, we get true. When the left side is false and the right side is true, we still get true. When the left side is false and the right side is false, we still get true. The only time we get false is when the left side is true, but the right side is false. And that's what we have now. P at 3 is true, but to the right implies to P at -1 is false. So the answer is false. Now, if I have P at 3, the same implication. This time, not P -1 is true. So this is true, because not P at -1 is what? False. So not false is true. So this condition now is true. So true implies to true will be true. Now, the expression with variables are not propositions and therefore do not have truth values. So for example, if I say P at 3 and P at Y, I don't know, Y is a variable. We don't know whether it's true or false. So this is not a proposition. Or if both are P at X, it applies to P at Y. Both are variables again. This is not a proposition. We don't have. Now, when used with quantifiers, which will be introduced next slide, these expressions, that is the propositional functions, again become a proposition. The quantifiers now will give us the condition of maybe or some. And that's what we're going to do next. So what is a quantifiers? Quantifiers make it possible for, first of all, we need quantifiers to express the meaning of English words, because sometimes we may have some, or so example here, all men are mortal, some cats do not have four. And that's the two we are going to use. So the two most important quantifiers are universal quantifier, which is all, for all. The symbol is upside down A. So this symbol represents all. Existential quantifier is some. There exists, not all, maybe some out of the population, we have some. And that's the symbol also. So we can write as in, this means for all X, P at X, and for some of X, P at X. So all X, P at X, assert P at X is true for every X in the domain. So this symbol means everything in X. But sum of X, P at X will be true if some of the X here is in the domain. Again, we're going to see an example in the next slide. So we have all X and some of the X. So this is example. We have all X, P at S, which is read for all S, P at S, or for every S, P at S. So this is the question now, first example. If P at S denotes that S is greater than 0, this means all the values of X is positive from 1 to 3 positive. So U is the integers. Then all S, P at X is false, because why? The condition is S greater than 0, but we said universal set, or U, is integers. Integers also can be a negative value, so we can have -10, -2, etc. So that's why we say all X, P at S is false, because some of the integers will be positive. Here we represent only the positive value, but some also can be negative. Now we say, okay, if P at S denotes S is greater than 0, and U is the positive integers, now here we are the domain, we exclude negative. So the domain of U is only positive. And since S is greater than 0, then all X, P at S is true, because our domain is only positive values. Here we say the U is any integers. So we have both positive and negative value for the first example. So it's false, because all X are not only positive, they have negative values. But here we specify the boundary to be only positive integers. So S greater than 0 is true for all S, P at X. Now if P at S denotes S is even and U is integers, again we are using all. We know if U is integer values, some of the values will be odd numbers, not only even numbers. So all S, P at S will be false. So next we talk about the sum. not all. Universal is all, existential is some. So here we are saying that sum of x, p at s is read as for some x, p at x, or there's an x such that p at s, or for at least one x, uniqueness, at least one. So let's see the example. If p at s donates, and we say s is greater than 0, which means these s values are positive, then u is the integers that now here not all x, we say some. So this will be true because some of the x will be positive and some of the s will be negative. So since some of the s is positive, then sum of x p at s is true. And the same thing, if we make it less than, it will be true because some are positive, some are negative. Now we say, okay, if p at s denote s is less than 0 and u is the positive integers, then sum of s p at s is false. Sum of s p at s is false. Why? Because now look here, we say the x is negative values, but the universal said there's no any negative value, it's only positive integer. So that's why this is false. Now, if p at s donate s is even number and u is the integers, then sum of s is true because here we say u is what? Integer value. It can be both positive, negative values. Some of the values will be even numbers. Some of the values will be odd numbers. So this is true. Now we also have the uniqueness quantifier. Uniqueness quantifier, we use the exclamation point. So here we say sum, not x, p at x, or exclamation. So this means we have only one answer. So it means that p at s is true for only what? One and only one x in the universe of discourse. So that's what we call the uniqueness quantifier. And let's see, an example here may even help us to understand. So for example, here we have, if p at s donate that s plus 1 equal to 0, and u is an integer, which means it can be positive or negative value, then what is the unique value that will make it true? It's only one value, which is what? Negative 1. Negative 1 plus 1 is 0. Apart from negative 1, any value here will never give us 0. So the condition here is true, but only unique, only one value can make this condition true. So that's what we mean that, again, sum of x, exclamation, and this, again, this is a symbol. The exclamation s sum, exclamation x means one unique, it's true for only one and only one x, one unique value or variable value will make it true. So thinking about quantifiers, here we say that when the domain of discourse is finite, we can think of quantification as looping. Finite means there's end to it, maybe from 1 to 20 or 1 to 10, or not 1 to infinity. 1 to infinity means, again, there's no end. So here we say when the domain of discourse is infinite, we can think of quantification as looping through the element of the domain and it to end at one particular point. So to evaluate that, all x, p at s loop through all x in the domain. If at every step p at s is true, then all x at p at s is true, which means in this case I have, let's say we are using s is greater than 0 up to 10. So I can say, okay, from 1 to 10, if we use that values 1, 2, 3 up to 10 to test the condition and all of them are true, then p at s is true and also all s p at s is true. If now at some step, one of the s value make it false, then p at s is false, then all s p at s also will be false, and the loop will terminate. Now also the same to evaluate sum of x p at x loop through all s in the domain. If at some step p at s is true, then sum of s p at s also is true and the loop will terminate. Now if the loop ends without finding an s for which p at s is true, then sum of s also will be false, which means p at s is false because we didn't find any s to make it true. Then sum x p at s also false. even if the domains are infinity, we can still think of the quantifiers in this fashion, but the loops will not terminate in some cases because it's infinity, there's no end. So these are the properties of quantifiers. Here we say that the true value of sum of s p at x and all x p at s depend on both the propositional function p at x and also the domain u, which is very important. So this is example, if u is a positive integers. Now u is positive integers means, let's say we are using a variable s. So we say if s is greater than 0, it's positive integer. And we have p at x is a statement x is less than 2. Then sum of x p at s will be true. Why? Because s is less than 2 means we have 1. 1 is positive. So at least 1. And 0 is positive. Then after that, we have the negatives. But at least since 1 is positive, then sum of s p at s is true. But if all the x will be false, because we have s less than 2, we may have negative value, -5, -7. -5 or 7 is less than 2, which is true. So all s p at s will be false. Now, if u is the negative integers, now our universal set means s is less than 0, negative integers. And p at x is the statement s is less than 2. Then both sum of s p at x and all s p at s are true. Because in this case, we can see sum of s p at x, s is negative integers, and the universal set is negative integers. And our condition say s is less than 2. So we may have some negative integers values here. And all s p at s, we may also have it. So here we say that if u consists of only 3, 4, 5, and p at s is the statement. One second, again, in number 2 here, my slide here, I made them. You see here, the condition said s is less than 2. So if s is less than 2, sum of s p at s is true. Why? Because all the u universal set is negative integers. So we may get negative, any negative value. So sum will be, but all s p at s will be false. Why is it false? Because if s is less than 2, then we have 1. We also have 0. And 1 and 0, they are not negative integers. So all s p at s is false. It's not true. It's false. Now here we say that if u, and one more time, the slide here, supposed to put false here and I put true. So we can correct this again. Where my cursor is, all s p at s is false. Why is it false? Because s less than 2, we also have a positive value 1. But the universal set or the domain of the values are only negative values, negative integers. So now let's see the next one. Here we have only 3 universal sets of our domain, which is 3, 4, and 5. So we say if u consists of only 3, 4, and 5, p at s is the statement that s is greater than 2. So if s is greater than 2, yeah, then all the values are true. 3 is greater than 2, 4 is greater than 2, 5 is greater than 2. So both sum of s p at x and also all s p at s are true. They are all true. But if p at x is a statement that s is less than 2, then both sum of s p at x and all s p at s are false. Now let's check if this is true. Look here, we have 3, 4, 5. Now, the first time we say everything is true. Why? Because 3 is greater than 2, 4 is greater than 2, 5 is greater than 2. So sum of SP at S is true, or SP at S also is true because all the 3 values are greater than 2. Here now we can see that S is less than 2. Same thing. Now all the 3 values here are what? They are all greater than 2. They are not less than 2. So this condition is false. So this will make both sum of s p at x and all x p at s to be false. Now let's go back to question 2, which I said this is wrong. Here you see we have s is less than 2. and the universal set is only negative values. So it will be -1 up to any negative value. But here we have at least one positive value and 0. So that's why all SP at S is false, not true. Because we have at least 1, 0, and 1. But all supposed to be negative. But some of SP at S will be true because it's not everything. We have any negative value is true. Now, the next section, we talk about the precedency of quantifiers. We always say that the quantifiers has higher precedency than the logical operators. Again, when we mention the logical operators, we mean the conjunction, disjunction, or and not. Those are logical operators. So example is give the quantifiers again, only two we are studying here, or sum, or universal existential. So for example here, we say that all x, p at x, or q at x means all s, p at x. So you see what is going on. When the higher precedency means that I have to use the quantifier first, get the result, then q before I'll use the or operator. So we get the result here before we compare with q at s. So again, the quantifiers have higher precedency than the logical operators. Now, next example, translating from English to logic. Every student in this class has taken a course in Java. How can I translate this to, again, the logic expression or logical expression? Now, remember, we talk about propositional function. We should have a variable and we should have a predicate. Predicate is more or less like a function, P at S. So in this case, I can say every student in this class has taken a course in Java. If X represents the students and J can be Java, I can have a predicate that J at X. J at X. And remember, all student, every student. So I will say all X, J at X means all students have taken Java class. So let's decide. Again, this question, we have two answers. Again, the question said we should convert or translate the English sentences to propositional logic expression or to logic. So here we said, okay, if U is all students in this class, basically every student in this class has taken a course in Java, U represent all students in this class, we are going to define propositional function J at X. J at X denoting X as taking a course in Java. So this will be translated as what? All students. J at X means students, S students have taken Java class. So here we get all X, J at X, which means all X is students. So all students have taken, J at X means student take Java class. So all students are taking Java class. Another option is we can say, okay, if U is all people, also define a propositional function S at X, denoting that S is what the student in this class, S at X, student in this class, because U means all people. Let's say in a school, we have 100 students, maybe only 20 of them are taking Java class. Here we are assuming that the universal set is, we are 100% sure we are dealing with all the students that are taking the Java class. That's why the expression is very straightforward. All X, J at S. J at S represents student taking Java class or all student taking Java class, our expression. Now, if we say U is not only the students, but all the people, some of them may take class, some of them may not take a class. So we use S at X at the students that are taking the class. S is the student in the class. So this will be translated that, you see here we are using implication. So every student in the class have taken Java class. So implication implies all students, S represent the student, and S at X means student in the class, J at S means have taken the class. Another question example is translate the following sentences into a predicate logic. Some students in this class are taking course in Java. So here we just use the sum instead of all. So we use the symbol sum. If U is all the students, then it will be some of the students have taken Java class. J at X is our student taking Java class. So some of the X students have taken Java class. Now, if we say that U is all people, as the previous example we saw it, if U is all people, then we translate this as what? S at X means students in the class and taking Java. So some of the students in the class have taken Java class, and that's what is some students in the class has taken Java class. So some X students in the class, S at S in the class, have taken Java class. So these two conditions have to be true. That's why we are using N. So we are returning back to the Socrates example. Here we said that introducing the propositional function man at X, donating X is a man, and mortar at X, donating X is mortar. So we can use the predicate function saying that, with quantifier saying that if man is a mortar, man at X is a mortar, which is all X, man at X implies to mortar at X, this is true to true. Then man is what? A Socrates. Then mortar should be Socrates also. So here, because we say man implies to mortar, all men, all X implies to mortar. So if man at X implies to mortar at X, so if X is Socrates, then mortar also should be Socrates. So this is the very good example of our first example we were giving about Socrates and mortar and man. Now we can write it again in a very propositional function or predicate function also. Our predicate function is M at X, mortar at X. In the later next section, we're going to discuss how to prove the concept, which will be our next topic. The next is equivalences in the predicate logic. We say that statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value. For every predicate substituted into this statement and every domain of discourse used for the variables in the expression. So the notation S and T indicates that S and T are logically equivalent. Until we study about this and propositional equivalency in our previous also. So example here, all X not S at X is the same as all X S at X. Why? Remember we studied this, not and not will cancel each other. Negation cancel each other. So all X not S at X is all X S at X. So this is equivalency in, again, predicate logic. So thinking about quantifiers as a conjunction and disjunction. Remember, we also studied in our previous lectures that negation of N is all. Negation of all is N. Actually, using the De Morgan theory. We went through De Morgan theory, and that's the concept here. So thinking about quantifier as a conjunction, negation of conjunction becomes disjunction. Conjunction is N, disjunction is all. And when we start the Boolean algebra logic circuit, conjunction may represent as a product and gate, and disjunction is all sum. So here we say that if the domain is finite, a universal quantifier proposition is equivalent to a conjunction of propositions without quantifiers, and an existential quantifier proposition is equivalent to disjunction of propositional without quantifiers. So if U consists of integer 1, 2, and 3, here we can say all X be at X is the same as, remember we have only 3. Our universal set is only 3. So all the X are 1, 2, 3. So it's the same as writing P at 1 and P at 2 and P at 3. So these two are equivalent. Now, some X P at X Now, remember we say some, not all. You see, the reason why we have these two difference that all always will represent conjunction or n. The reason why, because n means all the conditions here have to be true. All means only one of the conditions have to be true. So, for example, if I didn't have 3, remember some. So if at least 1 and 2 is inside, then it's true. So that's why, again, all statements always equivalent to end. Then some always go with all, because with all, only one condition have to be true. Some means not everything. At least if one value is inside the domain, then it's true. So these two expressions are the same. N means everything you have to be inside. That's why we say all. And that's why we are using the or symbol, or x, p at s, which means 1, 2, 3 is inside the u. Now, sum of s, p at s means it can be only 1 or 2 or 3. You don't have to be all. That's why it's sum. So here we say, even if the domains are infinity, you can still think of the quantifiers in this function. But the equivalent expressions without quantifiers will be infinitely long. So negating quantifiers expression, here they say consider that all x, j at x means what? All x. So every student in your class has taken a course in Java. So j at x means students taking Java class. Here j at x is s has taken a course in Java, and the domain is students in your class. Now, negating the original statement gives it is not the case that every student in your class has taken Java. So if all students take Java, negation will be not all students take Java. This implies that there's a student in your class who has not taken Java. So symbolically, we can say that not all students have taken Java. So not all S, J at S means not all students have taken Java. Or we can say some of the students, so existential, some of the students has not taken Java. So these two are the same. So you can see where the negation is. Because we can't put the negation is, if I put the negation is not some of the students, it means not everything becomes there's none. So here, not all X means some of the X has taken Java. Now, some of the X have not taken Java. So the two are the same. And we should pay attention where the negation symbol is for both. So De Morgan's laws of quantifiers, I think we went through this. And this is the rules for negative quantifiers. Remember that n negate will become all negate become n. So for example, here we have not all s p at x is the same as saying all s not p at x. Or not all s p at x is the same as saying all s not p at x. They are equivalent. So the reason this table shows that not all s p at s means some of s not p at s. Or not, and this means again not sum of s p at s, which means all s not p at x. This is very important, and this may make us get the whole concept that will take us to when we start to go through set concept also. So translation from English to logic. Here we have some students in this class have visited Mexico. Some students, so this means some students. X is students, and we use the existential symbol. So some students have visited Mexico. So S at S are the student in the class and then went to Mexico. M at S means Mexico. So here we say let M at S donate S has visited Mexico. Student that have visited Mexico. And S at S donate S in this class. So the students in this class have visited Mexico. We are using conjunction. These two have to be true. Both of them have to be true. It means some of the students have visited Mexico. So we use the sum. Now, every student in this class has visited Canada or Mexico. Then in this case, we're going to use all X. But remember, you see Mexico or Canada, not N. It's all Canada or Mexico. So we say some of the students in the class, S at X is the students in the class, implies to what? They went to Mexico or Canada. Now, if the sentence is said, every student in this class has visited Canada and Mexico, then we write M at S is students been to Mexico, and C at S means Canada. So students, S at X is students implies to Mexico or Canada. And here we say every student, so we are using quantifier or for all students in this class have visited Mexico or Canada. Another example, we have a universal set to be frigos, snots, and tingamapos. Again, we have a very strong three words here. Now we said that, okay, if F at X, S is frigo, and S at X, S is snot here, and T at S, S is tingamabob. We say that if any figure is a snot, then it is also a tingamob. So we have to translate this, and this is our solution here. Now we say F at S is frigo, S at S is snot, T at S is tingamob. Now the sentence is said, if any frigo is a what? A snot. So F at X and S at X is a snot. So N. Then implication. Remember we did this in the previous lectures, propositional logic. What implication? Implication means then. So this symbol means then, Tina Mogo, so T at X. And here we say if any. So we use all X. If any figure is a snot, then it is this. So all the X and the condition. So we can say this here, figure is a node, so it's N. They have to, both have to be true. Then implication, tinagamop. If any means all of them, so all X. So some predicate calculus, this is another definitions of a predicate calculus. Here we say an assertion involving predicates and quantifier is valid if it is true for all the domains and also every propositional function substituted for the predicates in that session. So for example, if I say for all X, not S at X, here I'm trying to, let's say S at S is a students in a class. So if we say all the students are not in the class, and here we say not some of the students in the class also. This is, again, we said it, double arrow means biconditional, so it can go both left and right side. So this assertion means, and this means this have to be if only the condition, these two conditions have to apply if only those two conditions. So here we're trying to say that not all students in the class, and here we say not some of the students in the class. So the two goes together. So we say an assertion involving predicate is satisfiable if it is true. So for some domains, some propositional function that can be substituted for the predicate in that session. Otherwise, it is not unsatisfiable. So let's say this one, the same condition we had previously. We say f at x implies, it was f at x and also s. So here the condition, if any figure is a snod, so f at x and s at s imply then is a t at x. Because we say if any figure is f at x, is a snod, which is s at x. So if f at s and s, then implies is this. Now our question here is saying that if all x is f at s, and this is by conditional t at x, which means t at x for f at s and f at s, so that's the only condition that will meet. This is not valid, but it's satisfiable, because if you are t at s, you can f at s, but there may be f at s and s at x applies to t at x. But this is not satisfiable. We say f at x and not f at x, f at s and not f at s, and this is not unsatisfiable. And we have more predicates. So a scope of a quantifier is a part of an assertion in which variables are bound by the quantifier. So here we have f at s or s at x, or x f at s or s at s. S has a wide scope, or s f at s. And now we have or s f at s or y s at s. So this s will have a narrow scope here, because all this is y variables. So this will be the conclusion of our lectures. And again, in these lectures, our main goal is to cover what is a predicate and also quantifier. So it's like a continuation of the previous lectures that we cover on propositional logic. This time we said if we want to write propositional function, we need at least variables, and also we need functions, propositional function, which represent our predicate. And we can use the quantifiers. The two most important quantifier is all or some. So universal or existential. So I'm going to end the lectures here, and again, wish everybody the best. Thank you.